contain within, like they can seem quite restrictive in how we use them, but they are incredibly informative in lots of different engineering problems. Actually, I've got a good example. I'll get to that later. We'll talk about that later. Oops, sorry, I'll move this over. Yes. So if we have a beam, whenever we have a beam, whenever we have an object, we need to think about the difference between the internal stresses and the external loads. So we're going to have a beam here, and it has some length in the x-axis. It will have some sort of external loading on it. That external loading can be arbitrary, but no matter how we break that beam up, if I have this is my beam here, that beam at the moment, it's in equilibrium. It's in static equilibrium. It's not accelerating in any direction. So that means, on the whole, that obviously this system, this expertly manufactured beam that I have in front of me, for it to be in equilibrium, obviously the sum of forces and the sum of moments on that beam need to be equal to 0. And that's not true just for the whole beam itself, but no matter how I cut that beam up, no matter if I look at, this portion over here, or look at this portion over here, if I cut the strip off the middle, if I cut this, when I go and cut it, if I go and break it up, then if I look at the external loads, here represented by W, and then when I go and cut it, you sort of think as when you go and cut it, you expose the internal stresses. The internal stresses sort of act, or not act like forces, they are forces. They're forces on the inside of the object. They will work to keep that system in static equilibrium. Stresses are just forces over area. So when you think about stress, you sort of also should be thinking about it as a local force in a very small area. So when we go and apply some sort of loading W, if we go and look inside of that object, that is going to generate some internal shear stresses and some internal bending moments. Right? Shear forces are obvious because obviously if we have some sort of force here, equal and opposite reaction, there needs to be internal forces to oppose it. We call those shear forces V, and this is how we define it to be positive. If I've made a cut, and if I'm looking on the left-hand side of that cut, downwards is positive. If I'm looking on the right-hand end of that cut, upwards is positive. And this is how, and if I ignore that one, if I just look at that left-hand side, this internal shear force here has to be enough to balance out all of these forces, as if I cut it that way. So if I have some forces acting on top of it, this internal shear force needs to be enough to balance out that the external loads. And the same thing in the way that we calculate, obviously, that is just sum of forces external minus sum of forces internal needs to be equal to 0. Same thing happens with moments. Because obviously, not only is this system not accelerating vertically, it's also not sort of having a rotational acceleration, so the sum of moments needs to be equal to 0 as well. And because we have forces distributed over a length, that will generate a moment, and subsequently, obviously, we need a moment being generated on the inside of it. And obviously, we generate with, just as we had a definition of positive here for the shear forces, where for the left-hand side it goes down, right-hand side goes up, left-hand side goes counterclockwise, right-hand side goes positive counterclockwise. But we'll go through a couple of examples just to make sure we get to understand that. So general process for this. Whenever you're faced with a problem like this, obviously we have external loads that are applied, right? These are loads. We also have points at where it's being reacted to. If this was just free floating in space, and if I applied some sort of distributed load here and a local point load here, and if I didn't have these supports, obviously it would just accelerate through space. So need to have some sort of reactions to it. So here we have two reactions. So the first thing we'll need to do is to calculate those reaction forces. Obviously we do that on a three-body diagram. And then we'll go and once we will know what those reaction forces are, we can have them applied, and then we can start going through the process of generating the shear force diagrams and bending moment diagrams. Right? One thing to note is that anytime you have there's this concept of discontinuity. What we would like is we would like to have it'd be a lot easier for us if we could just have one equation, or one relationship, which tells us as we move from this end here A to the end D, if we call that our x-axis, if we had just one relationship which told us as I moved in that x-axis, what was the value of the shear force and what was the value of the bending moment. Right? If I just had one relationship, that would be nice and easy. The issue becomes that because we have, obviously if I'm going to have a reaction force here at A, and then I have this distributed load, not a uniformly distributed load, but a increasingly distributed load, and that sort of abruptly stops. I can't have an equation, I can't have a relationship which just has that sort of abrupt stop, otherwise known as a discontinuity. So anytime you have one of those discontinuities, you need to have a new region or a new relationship to describe either the bending moment or the shear force values, right? So one really useful thing to be able to do is be able to look at a problem like this and think about how many discontinuities are there, and therefore how many relationships, how many equations do we need. In this example here, obviously we're going to have a reaction force at point A upwards, and between point A and point B you can sort of imagine that there's going to be one relationship of the shear force. Right? But as soon as we move from point B to in that region between point B and point C, there's going to be a different relationship. The relationship in this region of the shear force is different to the relationship in this region. So therefore we should have two different relationships. So this is the discontinuity here. We're going to have the same thing here when we move from region BC to region CD. There's going to be a different relationship again. Right? So for this system here, you can sort of think of it, as we said here, there are three distinct sections. There's these two discontinuities, there's one at B and one at C, and it's always, you can sort of think of it as being, the number of relationships you need is always the number of discontinuities plus one. Here we have two discontinuities, one at B, one at C, therefore we need three relationships. Because if you had zero discontinuities, you'd still need one relationship to define it. One set of equations. Yeah, and we'll go through all that. So this is just saying that inside of each one of those regions, we're going to have a relationship for the shear force, and each one of those regions, x1, 2, or 3, we're also going to have a relationship for the moment. As I said before, we can then look at developing we can then do sum of forces, sum of moments to figure out what the values of or what the actual relationships are for V and M, and that's relatively easy. So we'll go through and do that in a second. One thing I did want to say is there is always this a relationship between the internal shear force and the internal bending moment, and that's really codified by this thing here. So if you have the shear force diagram, one thing to note is if I start adding up the area underneath that shear force diagram, that is going to give me, or at least in like one continuous area, that's going to give me the value of the moment. So you can see here, when if this is my x-axis, obviously, at the start of it, the area under this x-axis is 0 because there's no length, there's just a height, and therefore the moment is equal to 0. But also, what it does mean is that the value, as I move rightwards on that x-axis, and the area increases, so does the moment. Right. In this region, the area, or the value of V is always positive, so that means this moment is always increasing. And you can sort of think of this area here where the shear force is negative, this is a negative area. So we have a positive area plus a negative area, or minus that area, so that means that this side's going to be decreasing. We have a maximum value of moment up here, and it's increasing to that point and then decreasing. And that point of the maximum occurs where the shear force is equal to 0. Another way of saying that is that the shear force, the value of the shear force at any point x, is the gradient of the moment. So here, the value of the shear force is 0, therefore the gradient is 0. Here the shear force is its maximum value, it's the maximum positive value. And here, that means that this gradient here, the slope, as it were, is that value, and that's the most positive gradient of M we will have. And then obviously here, because we have negative values, we have negative slopes, negative gradients. Which becomes very, very, very useful. And also, bear in mind that you can also do a similar relationship between bending moment and shear force as you do between shear force and external distributed loads. Bearing in mind that there's a negative side here, which we'll get into in a second. Alright, as said, it's good to do an example, and we'll try to do a bunch of examples. So, let's crack on with this one. So what we want to do with this is we want to draw the shear force and bending moment diagrams, and also figure out what the forces are, so label them. So being able to label where the maximum shear force is, where the maximum bending moment is, where the label is 0, and those sorts of things. With all these examples, I'm always going to give you guys a head start. So you'll have a few minutes here to start doing the problem. I want you to treat these example problems as if they were exam type problems. So start training yourselves, start getting used to going through it now. So copy down the relevant information, figure out what you're doing, start writing it down. Don't sit there looking at me, waiting. I'm not that pretty. If you want a photo of me, I'll send you one.